Why do atoms exist? That's a hard question to answer. Why are some atoms radioactive? That's an easy question to answer, what this lesson is about. The answer has to do with one of the four fundamental forces of nature, the nuclear strong force. The others are gravitational, electromagnetic, and another nuclear force, the weak force. Before we discuss the nuclear strong force, recall that the nucleus of an atom is composed of nucleons, which is the collective name for protons and neutrons. Each nucleon is composed of three smaller particles called quarks, believed to be fundamental, which is to say not made of smaller parts. We'll not treat quarks in this lesson, however. We've learned that electrons orbiting outside the nucleus emit photons when making transitions to lower orbits. Interestingly, similar changes of energy states inside radioactive nuclei result in the emission of gamma-ray photons. This is gamma radiation. We know that electrical charges of like sign repel one another. So how is it possible that positively charged protons in the nucleus stay clumped together? The answer to this question involves the discovery of an attraction in all atomic nuclei called the strong force, which acts between all nucleons, protons as well as neutrons. This force is very strong, but only over extremely short distances. About 10 to the minus 15th meters, the approximate diameter of a proton or neutron. Repulsive electrical interactions, on the other hand, are relatively long-ranged. We see here a comparison of the sample strengths of these two forces over distance. For close-together protons in a small nucleus, the attractive strong force easily overcomes the repulsive electric force. But for protons that are far apart, like those on opposite sides of a large nucleus, the repulsive electric force may be stronger than the attractive strong force. Then we have an unstable atom. Consider the distance between protons in this pair of nuclei. Although the art suggests nucleons at rest, they're actually in constant motion. Whatever their motions, all nucleons are close to one another in the smaller nucleus and all experience an attractive strong force. But in the larger nucleus, nucleons on opposite sides are farther apart, with a resulting weaker strong force holding them together. So which nucleus is more likely to be stable? That's right, the smaller one. An example of a light stable nucleus is helium-4, made of 2 neutrons and 2 protons. It is tightly bound. All 4 of its nucleons attract by the strong force, and only 2, the protons, feel a repulsive electric force. But this repelling electric force is overwhelmed by the attractive force of 4 nucleons. The presence of neutrons is a sort of nuclear cement. Neutrons add to nuclear stability. This helium nucleus is the same thing as an alpha particle, which indeed is a very stable particle. In contrast, back to a large nucleus. If it's uranium, each of its 92 protons feels the repulsive effects of the other 91 protons. The nucleus is unstable. We see that there's a limit to the size of an atomic nucleus. It is for this reason that all nuclei having more than 82 protons are radioactive. If these nuclei contained only protons, they'd fly apart big time. Why don't they? Nuclear cement again. The presence of neutrons, which outnumber protons for the heavy elements, keeps them together. Hence, we find that atoms near the end of the periodic table have a greater number of neutrons than protons in their nuclei. For light elements, it is sufficient to have about as many neutrons as protons. An isotope of lithium, lithium-6 for example, has equal numbers of each, 3 protons and 3 neutrons. For large nuclei, more neutrons than protons are needed. Uranium, for example, has about 1.5 times as many neutrons as protons. How nice that neutrons add to nuclear stability. Interestingly enough, however, a neutron by itself is radioactive and spontaneously transforms to a proton and an electron. A neutron needs protons around to keep this from happening. The alpha particles emitted in alpha decay are literally nuclear chunks, and it is mainly heavy nuclei that emit them. Beta and gamma particles, on the other hand, can be emitted by radioactive nuclei, both heavy and light. As a footnote, I should add that with beta emission are neutrinos and antineutrinos, tiny particles with near zero mass that travel at nearly the speed of light. So in summary, we see that in atomic nuclei are opposing forces, electrical and the strong nuclear force. Electric repulsion occurs between protons, and the strong force occurs between all nucleons, protons and neutrons alike. Whether a nucleus is stable or not depends on the balance between electric and strong forces. In elements beyond 82 in atomic number, the balance is tenuous, and these atoms are radioactive. In the next lesson, we'll look into the transmutation of atoms that occurs when undergoing radioactive decay. For now, I want to leave you with a question. In the nucleus of ordinary hydrogen, does the strong force play a role? How about the electric force? Until next time, good energy.